Okay, you will see now. That's something that I gave you, I believe, and I don't know, the direction does not matter, but let's assume that the direction of this was like that for now. So you will figure out the direction of, this is a closed loop, all right? It goes like this, and like this, and like this. So the key is what is gonna happen with this part. So I need to ask your thoughts about that.
They're gonna cancel out each other?
Yeah, because they are so close that they keep, because they are so close to each other, they will cancel out. It's like you have almost like one current opposite to the other, and they are almost in the same position. Another way to understand that, because we discussed that in class, if you have two currents, one going like this and the other going like that, we said that the field will practically concentrate here. So it's very localized. The closer the two wires come, so if the two wires come even closer than this, if the two wires say, let me see, go here. If the two wires come to be closer, then this field will also concentrate like in here, a smaller and smaller region. So practically, if they come almost one top of the other, like here, then the field concentrates only here. Well, this one. So practically, it's like for the rest, the whole field here is gonna only concentrate in this area, which is so small that practically does not exist. So the only thing that allows you to do is to consider that this is equivalent to two loops, one like this and the other like that. And you solve that problem. Okay, so that's as a hint for homework.
Excuse me, Professor?
Yes.
Do I have to write like the explanation why they cancel out each other? Because I just solved it like assuming that
No,
they, okay.
assuming that they cancel, just say it though.
Okay.
Okay.
Okay, sure,
Yeah,
thank you.
don't have to do any, I mean, the explanation is for you, It's like something that I'm doing so people understand why I cancel them. We consider they're not there.
Thank you.
Sure. Any other questions that you think that will help you with this problem before we go to solving other problems for review?
Professor?
Yes.
Yeah, so I actually was a little bit confused by this problem. By the way it was showing, I was getting the impression that the whole thing was just one wire, because the problems
It
is
is
worded
one wire. It is, the whole thing is one. What do you mean one wire?
I mean, like like it was a rather thick wire that just didn't
You thought
touch
it
to
was
each other. So I assumed that I would need to find the current density and then kind of integrate it as if they are small wires. And I integrated that like towards the
but
center.
did you not see, what do you mean? I mean, could you, can I see, because the current, did you see the direction of the current?
Yeah, it only showed one arrow, so I assumed that it was a little bit weird, but I'm just saying that
I mean, okay, let's
suppose
assume
it was one thick big wire.
yeah, but where would how would the current go? I mean, that's what it showed. So how would the current go if it was one thick wire with a slit? If that's what I just, is that what you told me? There was a thick wire with a slit in the middle?
Yeah.
Okay, but look at the direction of the current. Why would the current go like that?
Well, I'm not. I'm a little bit. I mean, I'm a little confused why the current would go the way it is with just thin wires and the way it's because there's no way, no ground or supply
Yeah,
for
it's
it.
one closed path. How do we assume here that there is one current in one loop? All right, we took a loop. Let me take a loop, what we did in class. And we assumed that was one current. The loop can be like this, can be, there can be a loop, not that we did not consider because it's difficult, they can be a loop like this and have one current. Who says that the loop always has to be circular? All right, what the loop has to do, the only reason we cannot consider these loops is because it's difficult to consider them without going to the computer. A loop can be like this, like an 8. That's a loop. If I were to show you this as one thick wire, let me just erase that part for a moment. Okay, let's assume that I was consider that to be one thick wire like this. Is that what you mean? Like a thick metal piece.
Yeah, I think I see what you're saying now. My apologies. I was just. I understand now.
Have you submitted your solution?
No, not yet.
Okay, then you have time to fix it. Because let me tell you why that cannot be what I have here. That cannot be what I have here, because where would the current go? I mean, if the current was going like this inside, where would it close? I mean, would it
Right.
go like this and then go like that and then stay open? Cannot be like this. If I could have given you something like this, but the current in there would have to go like that, either come out like in an infinite way or go in like this. But it would have to go to the direction which comes out of there. It would not be like this, therefore, in this case, if I wanted to give you something like that.
Right. Okay. Thank you.
Okay, you're welcome. Let me see, I'll remove those. There. Okay, any other questions about this? All right, you can ask me, keep that in mind, and ask me if something comes up. So what I would like, yes?
I had a quick question.
Yes.
I'm a little bit unsure of like when we use, I mean, because this is more of a general question than just the homework, but a little confused about like when we use H versus B.
H
So
versus
what exactly was the difference between the two?
Okay, first of all, by definition, they're different. All right, so one, and the units make them different, and I will explain to you. So H, the same thing, I will do both for magnetic and electric fields. So you see, because what you're asking me is true between D and E, and it's true between B and H. All right, so if you have a question about one, you will probably have a question about the other. So here is what I will write also for a review for you guys. That's why I'm writing it clearly. It's a good question, as a matter of fact. So that's why I'm taking my time. I'm sure that others will have the same question, may not be able to articulate it the same way. So in electrostatics here, and magnetostatics, we have the following. We start with forces. First of all, I'm not going to go too much in the forces, but just to remind you that what we feel, the one thing that we really feel is the force. So electric force here, magnetic force there. All right. Electric force. Now, from the electric force, from Coulomb's law, or we just, I'm not going to go there yet, but from the electric force, we define the electric field. Oops. So the electric force defines for us the electric field. How do we define the electric field? We define the electric field as E equals F sub E, the electric force, which is we feel, that's the one thing that we feel, divided by Q. And that Q, it would be, say, if we were, the only way for me and you to feel an electric force is if we were charges, or if our body, it was not neutral electrostatically. We would feel a force if we were carrying a charge, okay? And if our charge was Q, then from the force that we would feel, you can divide that with our charge that we had Q, and that would give you the electric field. All right, so that is electric field here. Electric field. And in some book, you will see also the word intensity in there. Not everywhere, but that. And the electric field is a vector. Now, from the electric field, we define the other vector D, which is epsilon E, and epsilon is the dielectric constant of the medium, or the dielectric permittivity, of medium. Of medium. All right, and D is called the electric flux density. And then we will explain where that is important. So now this is what we have defined, all right? Both D and E are vectors. The only difference is that these vectors are separated by an important constant. And this constant is the dielectric permittivity of the medium. And dielectric permittivity also, you need, now it is important to remember the units, because there is a differentiation there. The units for E are volts per meter. The units for D are coulombs. All right. And why? Coulombs per meter square, in fact. All right, these are the units. So that is, let's do the parallel, and then I will come back to how we utilize these quantities. So let me also put this one here. Now I'm going to the magnetostatics. In magnetostatics, we have F sub m. And from F sub m, we have now the entity that creates F sub m. If you remember, we have here, this one was practically QE. All right, from the relation before. F sub m is nothing else but Q V, which is the velocity of the charge, cross B. Okay, that is how this is defined. From B, so now practically, while from F sub B you have E, which is the electric field intensity in volts per meter, from the magnetic force F sub M, you have another entity which is B, and B, from B, well, it's obviously B is given by this expression, all right? So where V cross B equals F sub M over Q. So the equivalent expressions. Now, B, because of units, is not a magnetic field, even if we make reference to it as such, but in reality is a field and is a vector field and is called the magnetic flux density. And B is measured in amperes per meter square. From B, we define now another entity, which we call the magnetic field intensity. And the relationship that connects B to that is mu H. So where mu is the magnetic permeability of the medium. Okay, and now in terms of, we found one here in terms of units. For that, okay, this one. And now from H, where H is, so H is B divided by mu, then H has the units of amps per meter, all right? And H, in fact, is called magnetic field intensity. Now, that's how it was done. It's done. But there is one thing that you need to keep in mind, that even if we found B, we defined B first, what we have is that entities that are dual is not B with E, but it's B. So the entities which are dual, so duality here between the two static fields. So duality here says that F sub B is the dual to F sub M D, which is in coulombs per meter square, is the dual to B, which is Webers per meter square. E, which is in volts per meter, is equivalent to H, which is in amps per meter. Epsilon, which is in farads per meter, is equivalent to mu, dual to mu, which is in henries per meter. That's how the duality applies. So other than the forces that are clearly different, a lot of times when we talk about electric and magnetic fields, we may talk in general and then we mean either one of all of these, all right? So when we say an electric field, we may mean D or E when we speak, or we say magnetic field, we mean B or H. However, the fact that their units are so different give them very important, give them a significant importance. So for example, when we want to find capacitance C, all right, we want to use Q over V. But Q is equivalent to D, all right? Q is related to D. Q over meter squared is related to D. So C, D indirectly relates to D. So from D, we find C. From the electric, therefore, flux density, D, we find C. Now, the same thing here. Inductance is related to total flux psi divided by the current. And psi, which is the total flux, is related to B. So practically L then, to find L, we need to, we need to have access to B. So B in reality is gonna give us the ability to calculate L. So you see that even if we talk about electric and magnetic fields, and both E and H and D and B are important, when we are to calculate these equivalent circuit components, which is capacitance and inductance, then what is important in this case is D, so the electric flux, density, of course. And what is important here is the magnetic flux density. And what do they represent? Now, these are all in terms of math and everything. But in your mind, what should you think? How can you visualize D and B? So here, how you visualize them. If you were, say, an electron, how would you visualize D? So if you have here a charge that is producing an electric flux that is like this, that means that if you were an electron, or not an electron, if you were like a positive little particle that would come, one very small particle that would come somehow in this region, would be placed, then D for you would be the line you would follow to run away from this Q, if you were a little q plus. All right, so your D would be the path you would be forced to follow as a little charge to run away, because you will be pushed away from this positive charge, and then you would run along a D line. All right, so your line will be your D line if you were a positive charge. That would be your path moving away. That would be your how you would go away from the positive charge along this straight line. Now, if there was a positive charge here, as you did before, like a positive charge here, and a negative charge equal to it. Q, and Q. And you were a positive little charge, lower Q, thrown in somehow in between the two. Then if you were thrown here, if all of a sudden, one moment, you find yourself there, then your path would not be like the other one, but your path would have been this one. And the path then you would take away from the positive plus and into the negative, it would have been more symmetric, obviously, because, but so we'll do like this. Whatever, this is my, so it would be, and that is a D line. That's how we would sketch D. So always think of the flux, of the electric flux density as a path you would have to follow if you were a little charge inside that electrostatic field that is generated by a source, obviously charge. Same thing applies in magnetostatics, even if in magnetostatics we don't have charges, all right? There are no magnetic charges. They're only moving, electric charges, not magnetic charges. But let's assume that you have now a current here. And this current creates a magnetic field. And this current creates that magnetic field. And then here is gonna loop. Okay. That's how the magnetic field lines, then flux. That means that if I were thrown into this magnetic field, where the magnetic flux lines were like this, so the magnetic flux lines were like this here, B, and if I was there a moving charge, all right, since those exist, and I would be thrown here with this velocity, I will be, so let me continue this line like this. If I would be thrown here, this is a charge, and I would be Q, small q, and I will be thrown here with a velocity like this, then I would force myself to go on an interesting path that looks like this. So I would come here and start following this little path forever. All right? Circulating perpendicularly the magnetic field lines I found on my way. So in essence, that's how you should see, I mean, put yourself in a small charge position. In one, it's a static charge. So your electric flux lines show you the trajectory you will have to go if you were thrown in there in one position. For magnetic fields, if you were a moving charge, think of yourself of the orbit. So this charge is going to start orbiting in this magnetic field forever around these, you know, magnetic field lines from the source. That's your source here. All right, that's your source card. Then so you would be orbiting around that because of the magnetic force. So in essence, that's how you should see the meaning of the two, all right? This in reality is the meaning of the two entities. So they are not just mathematics. Mathematics, yes, I mean, mathematically we introduce them, so it helps us. but also they have, if you want to find meaning to it, this is the meaning that they have. So in essence, that's the difference between B and H. The B is a totally mathematical field. Excuse me, H is a totally mathematical field. We just created to create Maxwell's equations to give a mathematical foundation to the phenomena. E is also the same thing, is a mathematical entity. We created E and H to give meaning to what we see or what we feel. They don't really exist. They are mathematics. I mean, if there were people on another planet that would observe the same phenomena, it is possible they would not have E and H, they would have something different, trying to explain the same phenomena. So it's not like E and H is a real thing. They are mathematically derived. However, D and B, they have physical meaning. There is something we can describe in ways that we can see. I mean, you can run an experiment and see what I'm telling you. If you have a particle that was not only charged, but also illuminated, if somehow this particle could radiate some light so we could see it, then you would see exactly what I told you. The particle going along a D line for the first one, and the second, the particle orbiting around these lines of the magnetic field, B, magnetic flux density. I'm sorry if it took too long, but I'm trying to explain it for you, and I don't know whether I am successful though in the explanation.
I think this made a lot of sense.
No, try. I know it's difficult, and that is the most difficult thing to visualize, you know. That is the most difficult thing. The moment you feel comfortable with that, and comfort comes with time. I have to tell you, you're not gonna finish this class, even if you get an A+, for example. You will not finish this class and feel now comfortable that you really think and feel the fields. It takes time. It took me years of taking classes. However, it's always important to build it on the right things, all right? To build your experience with the electric fields in the right foundation, slowly building it up until in your careers with experience and both in classes and with work, you will start feeling comfortable with specific things. So you're not expected to understand all of this and feel comfortable. And the way somebody who is many more years ahead of you in this area. But that's the beginning, all right? So we start describing it as much as possible, you know, the way we can think about it. Okay, so with that, and a review of the fundamentals, any other questions before I start going to specific examples?
Yes, please. Excuse me, Professor.
Yes.
So, for example, in the homework, it asks for the magnetic field. So for this, like, do we find, are we supposed to find B or are we supposed to find H? Because there's another example in class where we were asked to find the magnetic flux, and you found B. So I'm a bit confused, like...
What does the problem tell you? Could you read it? I don't have it in front of me. Just tell me what it reads, how it reads.
Do you mean the homework?
Yes, yes.
Oh, so the homework, I remember for part 1, it was asking, it says find the magnetic field at the center of the loop.
Okay, yes, that's so when I say magnetic field in that case and nothing more, I mean H.
H?
Yes.
Oh.
Usually B, I call it the magnetic flux density. Not the full, not the total flux, because the total flux is the integral, right? Just the density. If I said, now, if you were to find, however, to tell you the truth, if you were to find B and say, this is my magnetic field, I would consider it correct, even if I would put a note and say this, we normally call it the magnetic flux density, more formally. But it would not be wrong, because a lot of times when people talk, say, for example, when you and I had to solve a problem and I come and I have a discussion with you on how to do it, and I say, I think we need to find the magnetic field. I can say that correctly, and I may mean B, not H. But when I write it down, if I were to write a paper, if I were to write a report, I will name it correctly. I will say, if it were B, I will call it a magnetic flux density. But since I told you find the magnetic field, period, at that point, that means H. Then what else does it say? Does it say anything else? Or is it all? Is that
So
all?
that's for part one. So for part two, it asks for the total flux through the area of the small circle.
Okay, so in that case, to be able to find the total flux, you have first of all to go from H to B.
Okay.
And B will be H multiplied by a scalar.
Right.
All right. So you will have to be careful about that product and the units.
Okay.
And then you have to integrate B to find the total flux.
Right.
All right. Yeah.
Okay, I get it. Thank you so much, Professor.
You're welcome.
Professor?
Yes.
Yeah, the way I understand the relationship between B and H, it's a lot like the relationship between current intensity and just current density, where if there's a uniform line of magnetic field coming from a uniform line of charge, then therefore in that case the B would equal H, kind of, in the same way that I would equal J if the line was a finite filament. Am I thinking about that right?
I would say that would not be how I would encourage it. Because, for example, if let's go to charges. If I have a charge, a total charge, which is like a distribution of other charges, then this total charge will create both an electric field and a electric flux density. And the individual will also have electric field, electric flux density. If you go, say, to currents, and you have a current filament, that will produce both the magnetic field, which is a mathematical thing, will produce a B lines. All right. So in reality, if we could see B, if somehow we could see those lines, if we had sensors on our head that would help us see that, we would see B, we would not see H. We don't have those sensors, so we cannot see it practically. Another species on another planet could, for example. Now, that applies for a filament, but if you had also a total current, each of the filaments that make you the total current that says is over an area, also those will generate both a B that will be the superposition of all of the B's of the small of the filaments, and therefore from that B will have an H. All right. So it's not like that one produces a B, the filament produces a B, and the total current produces an H, or the other way around. No. So every current, whether it's a filament or whether it's a distribution, produces a B. And from that, we extract H as a mathematical outcome, if you like.
Okay. I think so. H is basically the perpendicular direction in which the magnetic density B sorry.
So let me ask you this. I'm sure you have seen an experiment in maybe high school where you throw, you have two magnets, all right? And then usually magnets create flux lines. They have those lines, the magnets. You take two magnets. And then you put the magnets below a paper, and on that you throw chips of iron. And then you see them going along specific lines.
Yeah.
Well, these are the magnetic field lines. So we cannot see them, but in reality, they exist. Why do we say they exist? Because if you are like a little, if you can become like a little magnet itself, that you're going to be oriented along those. But that's the only experiment where people can, they call them in reality the magnetic field lines. They are the flux lines, what you see in that experiment. So I was going to say, yes, they're always, so all of these lines, the magnetic field lines, they are perpendicular to the area of the loop of the generating current. Okay, if there is, I mean, at least around there, on the loop, they come to be perpendicular, and then they go around in different directions depending on the loop, because they're going to come back and close. So for example, if you do you see this one? If you have a loop like this, a loop like, if I have a loop like this, and then I think it's a thick loop. So then the magnetic field lines around it will go. They will start perpendicular on the surface, all right, like this. And then they will turn around so they can close. They don't cross if they're coming from the same. Those lines do not cross when they come from the same generating current. You can have crossing lines only if they come from different currents. Okay, go like that. So they are always perpendicular to the area of the current loop, but they turn away, so they eventually close as paths. They are not open paths. And this, in this particular case, the current goes like that.
Right. I guess my question was, so the magnetic flux density B,
Yes.
that's going to be perpendicular to
Yes.
the magnetic field lines, right?
No. B and the magnetic field lines are the same direction because they only differ by a scalar.
Okay.
B only perpendicular to the area of your loop. And let's assume that this is the area of my loop. They will be perpendicular there as they pass, as they go through it. But B and H, because they only connect through a scalar entity, this is scalar, these lines for B and H are parallel everywhere. They just have different values. That's why I'm saying, think of B, don't think of H. Think of B, that's the real thing. And then consider H to be a mathematical outcome.
Okay. Thank you.
You're welcome.
Hey, I'm sorry, Professor. I think I'm just confused about the homework because the way I solved that, I derived the formula of B from the Piot-Savart law of the current loop, and then I found the B, the electric field, which is I thought it's gonna be B for both loops and added
There is no electric field.
the magnetic field.
Yes. Okay.
And then I added them together. But now you're saying we have to use H, but like
No, I did not say that. I said you can use either B or H. I
so,
said you can use B or H, but if I ask you for total flux, you can only use B. Because
so
B is the magnetic flux density.
yeah, so for the first part of the homework, we can use either B or H, right?
Yes, correct.
Okay. And then
And
the other one, the second problem, we're gonna find, psi, which is like the
yes,
integral of B.
but psi comes from B, all right?
Yes.
Yes. Okay.
Okay.
Yeah,
Thank you.
absolutely. Yeah. Okay. Any other questions about anything else that is important to your understanding?
I had a question about the homework. So just one
Yes.
more. I think you explained earlier, but I wasn't here. Can you explain why the inner loop and the outer loop goes in different directions for the direction
If
of the
you
current?
were, let me ask you this. If you were to consider that this is one loop, for example, look at the 8. You see this 8 shape? This is one loop,
Yeah.
all right? If you were to draw the current that flows into one loop, how would you draw it? The current has to flow in the same direction along this loop, all right?
Mm-hmm.
Yeah, how would you draw it then? Would you not draw it, if you go back to our loop, would you not draw it the way I did?
Oh yeah.
See, because if you draw it separately, then at some point the two currents will come to hit each other.
Yeah.
And
Oh,
that's
okay.
not true. That's not good.
That makes sense. Okay.
All right. Look at the 8. They look opposite because of that, because the current is like an 8 loop and it goes around like this. Think, you know what is the best way to think of these loops? Because I was looking these extreme parks, extreme parks when they have people moving around on these kinds of things that look like that. There is this, on my Facebook, I found this theme park that have this extreme kind of thing, where people are on cars and the cars move around. Well,
Yeah.
they move around on a closed loop.
Mm-hmm.
They don't go opposite directions. They have to move around like that. Otherwise, they would hit each other. If one
Oh yeah.
car, all
That
right,
makes
so
sense.
it's the same kind of thing here. Consider the current like this, like all of these loops in a theme park.
Yeah. Thank you.
Sure.
Hey, Professor, sorry, just going back to homework and just thinking about it right now. I don't have any question about solving it. Just when the current gets close to those two, to that slit, right in the middle of that loop, wouldn't they want? I guess I'm a little bit confused because wouldn't they want to? Just thinking about the charges as they flow around, wouldn't they want to slow down between there, and when it went to act like a capacitor? Well, actually, and
Yes.
not a capacitor because those involve opposite charges,
In
but wouldn't they at
reality,
least slow down at
reality,
that point?
absolutely. In reality, if I had, say, now we are solving ideal cases, all right? We have ideal wires. And we don't consider charge accumulation anywhere, either for statics or magnetostatics. But in reality, if, say, I had a microstrip, all right? Let's assume that my loop here was a microstrip loop. Like you know how microstrip is? Let me add this, add a page. So let's assume that I had the above loop example. So the above loop in microstrip form, which we are going to see in the rest of the for transmission lines in microstrip. Microstrip is something we create on printed circuit boards. How does a microstrip look like? A microstrip has a ground. Okay, it's a metallic surface on which there is a substrate. So practically there is a substrate with a metallized surface underneath it. And then on top of it, there is another line. Okay, that's a microstrip. It operates like this one operates like one. Consider that the current flows here like this, and there is a return current that flows here like that. We are going to see that later. But for now, forget about the microstrip and assume that this is just a strip, or like a strip, single strip, which it's like, in reality, that's what you have. I would say microstrip for a moment, okay? Because I don't want to tell you things that they don't work. All right, let's now assume, look at the strip from above. And this strip that I have, I made it exactly this way. Let me think. All right, so practically I did. So in fact, let me do it better than this. I'll show you how I'm gonna do better. I'll do something like this. And then I will do it very thick. Okay. And then I will do the other one like this. And then I will do this one and this one. And then I will make white all the in between. Let me see. Oops. Okay, first of all, this one. Like this, and then I will go to something very narrow and do this one. Okay, let's assume that that's your, and then you have a current that flows here. And the current flows like that, like here, here, and here. All right, and then all around here. All right, yes, what happens here is these two metals in microstrip form will look like this here when they come very close to each other. They will look like this. And it is true that the field in between is going to be so concentrated, the field, the lines will be so concentrated that practically the only place where there is a magnetic field is here. The only place where there's a magnetic field. However, as you said, what happens is these lines are so close, so you have a capacitance between this part here, this part of the conductor here, and this part of the conductor there, see each other, which means there is going to be field lines going from one to another. Electric field lines now, all right? Because they see the charges. Even if the charges move fast, they will see each other because it's so close, and this will create a capacitance because the charges will see each other, which means that these two will have a capacitive effect. There's going to be a capacitive effect here, which means that as the charges move through this area, they will slow down because they're going to be charged. They're going to charge this capacitor. and then they're going to be released. But this capacitor is going to be kind of small, so we don't pay attention to it. All right, if it's happening because the lines are thick and because they see each other like that. But if you have two infinitesimally small currents like that, the capacitance is going to be minimal. One where the current goes like this and the other when the current goes like that. So the capacitance between these two, because also we don't consider that there are metal lines and everything. Yeah, it can be considered to be not important. But in reality, yes, you do have that. And that's why you avoid in reality, you know what they do, people do for spiral inductors, because you need these kinds of things. You need these kinds of loops to create inductance. How do they make them? That's very interesting, because I had in mind to tell you, but then I thought maybe too much. You know how I would create this one so I don't have that kind of capacitance? I would go and put the center conductor the way it is. And then I would put the external conductor if I want it. But then there are two things that I would like to do. I would like to change the direction of the current, because if the currents have opposite directions in between the small loop and the upper loop, then they cancel part of the field. So I would like to change that. And so I would like to get rid of that capacitance. So what I want to do in this one is have the same direction of this current here, and I'm going to have the same direction there. So what do? I do the following. Let me see here. I have these two areas, all right, that I need to connect. But I'm going to connect them in a way that, number one, the current remains the same direction between the two loops, and then the capacitance, this capacitance go to zero. So look at what I'm doing in design. I'm starting here a little further out. Like to start a little further out here, a little further out here. And then I go from here there. And then I go over the other line. So I'm using another also layer. And I go from here, in a lower layer. So you will see a lot of these kinds of loops that are using for inductors in high frequencies. So number one, if you do it like this, the currents keep their direction. And also, instead of having these long two sections of lines to run in parallel and create a lot of capacitance in between, because these capacitances will be in parallel and they will sum up, what I do is that I have one line that goes like this. I have another line that goes underneath it like that. And the only area where they have overlap is here, so the capacitance is a lot smaller. So practically how this goes,
it's 2 o'clock,
is that goes is like a dielectric with a metal at the back. In microelectronics, always there is a metal. And then right at the intersection of the two lines, I have two dielectrics, and one dielectric is here. Then the other dielectric is here. And when they interact on here in this area, all right, it's going to be only for a section. So in fact, they're coming perpendicularly. So it's going to look like this. So it's going to be only this little area of overlap. Then it's going to give me this capacitance. This capacitance here is going to be much smaller than this one here. See? And that's what I have now. How do you go from one layer of the line to another, they use via holes. So practically at some point here, you will need to go through the dielectric and connect. So they use, if you want to connect from one line to another, if you have on a multi-layer substrate lines and you want to go from one line to another, and this other line is here, usually you open a hole in the dielectric and metallize it. And that's how you go. That's called a via hole or a via. It's metallized. So that's how people do it.
Okay, thank you. That was interesting. Thank you.
Yeah. Any other questions about the homework?
Professor, I have a question, but it's not about the homework.
Yes.
I'm having trouble interpreting just exactly what the phi component of a cylindrical vector is.
Ah, yes. Mm-hmm. Do you want me to do it for a particular problem?
Yeah, so I'm just wondering, like, what does it do to the vector?
Ah, okay, then let me start with something more fundamental, all right? Mm-hmm. So we're talking about a cylindrical coordinate system. So cylindrical coordinate system. Okay, so a cylindrical coordinate system has three components: Z, which is always along the axis of the cylinder, Z, along the axis of a cylinder, and usually the cylinder, and then let me do the Cartesian, because that's a point of reference for us, all right? We all feel comfortable with a Cartesian coordinate system. We all feel it. Is that right? Do you guys think also the same way? I feel very comfortable with the Cartesian coordinate system, cylindrical and spherical. I need to think about it. How about you?
Yes.
Yeah, same. Yeah. I know everybody has that. So here is the cylindrical. And in the cylindrical, let's see what kind of, if I were to find the cross section between my cylinder and the Y direction and my cylinder and the X direction. So let me draw it carefully here. What I would see, the cross section will be another circle similar to the top one, all right? So now let's assume that I have a point here. And I will do this point in two different ways, but let me start with this. Excuse me. Let me start with this one. So in this location, also one other thing. In a cylindrical coordinate system, always your point has to be on the cross section between the cylinder and the X, Y, and Z system. And why is that? Because you can put the X and Y, since Z is always the axis of the cylinder, and this is cylindrical. If you have freedom and people have not told you where to put your X, Y, which is possible, then I would normally put the X, Y plane to pass through my point of observation, all right? Always. So in this case, if you come and tell me, show me what are the components, say, of an electric field E at a point P, I mean, how do the phi, rho, and Z components coordinate things? Then I would say, okay, let me put the X and Y right where my P goes so I can explain it better. And that's why I put it here. So now there are three components that point P has. If I was looking at an electric field at point P, I will see three components. And what would I see? E sub rho, and I will come and show you each one of them. E sub phi and E sub z. So practically, let's assume that my E sub rho, what is the direction of the E sub rho component? To find the direction of the E sub rho, I connect the center to this point P, and it's this direction, and I extend. So it's along the radius. So this is my E sub rho. Let me move P for a second. Then what is my E sub phi? E sub phi is going to be perpendicular to E rho, tangential to the circle. So E sub phi is going to look like this. And what is E sub z? E sub z is going to go through my point. It is going to be perpendicular to both E sub rho and E sub phi. So this. All right. So if I look at this point, I see these three components. Now, what is different between an X, Y, and Z system and a cylindrical or even a spherical? Let's try now to have 2 points. This is point P. Let's try to have 2 points and in X, Y, and Z, and 2 points in the cylindrical. So here I will do it. Let me do an X, Y, and Z here. So if I had the same point here in my X, Y, and Z system, but I keep the same 3 components. So at this point P, I will have E sub rho like this. I will have E sub z like this. And I will have E sub phi to be like that. Okay. But what I'm going to do for comparison is to not keep in the coordinate system, X, Y, and Z, the same 3 components, but find the equivalent X, Y, and Z components, because obviously I can find the electric field in any coordinate system if I want. So practically here, if I were to express the field at the same point, but in terms of coordinates X, Y, and Z, that I would find E sub X, E sub Y, and E sub Z. Okay, so this is same point P there and P here. Now let's assume that in both cases I find another point. I find a point A. And let's assume that I am on my point A is up here. It's a different circle, all right? Okay, if my point A is, let me see, A, then I would have to find E at the A position. So I will have to connect, find the radius, and then that will be E sub rho for this point. Then I will have to find the phi, which is tangential to the circle, going through A, which is this, and this will be E sub phi. And then the E sub z will be like that. Okay, now I find the same point A here, and then I write the 3 components, but the X, Y, and Z system. X, Y, and Z. In all 3 cases, the total field is the same. For example, this is point A. Up here, now I'm writing E sub A, and this is E sub P. All right, let me put P here, P and P, so we remember. This is E sub A, and E sub A will be E sub rho A sub rho, plus E sub phi A sub phi plus E sub Z A sub Z. All right, now I will do the same thing down here. E sub A is going to be the same no matter what, whatever coordinate system I'm using. So E sub A, however, is going to be here the three other components, E sub X plus E sub Y plus E sub Z. And P, E sub P, will be E sub XP plus E sub YP plus E sub ZP. Okay. E sub A is here, is the same with E sub A there because there are the same 2 points, but I just used 2 different systems. So practically, I can say that this one here and this one there are the same. Also, I can say that this one here is the same with this one there. All right. Now observe this interesting analysis that we've done and tell me, if you were to sum the two somehow, even if they are not in the same, but maybe not some because they're not the same. Look at the two. What is unique in the cylindrical system and what is different between the cylindrical and the Cartesian when you look at how we have identified the components? What is something interesting as an observation, which is also very important? That in the Cartesian system, all of the X components are parallel. So this X component of one is parallel with this X component of the other. All of the Y components are parallel. This is Y. So this one of P is in the same direction with this Y component of A, and all of the Z components are parallel. Okay? So if A and P were to overlap, I could simply sum all of the X's, all of the Y's, and all of the Z's, and I can find the total field. Do you agree? If they were one on top of the other.
Yes.
Yeah. But what happens in the cylindrical system? Now that I've made that observation in the Cartesian, what is your observation for the cylindrical? That only the Z components align. What happens to the rho components and the phi components?
They're
In
not the
different directions?
same. Yeah.
Exactly. So if points A and P were to be on one on top of the other, I could not use the expressions of the relative fields in the cylindrical coordinates and sum them up. See?
Excuse me, Professor?
Yes.
Is that why you said once for a homework assignment that we couldn't add or subtract like the vectors and so? Okay.
Yes. So if you want to sum electric fields or magnetic fields at a point, because they come from different, say, sources, then the only way to do it correctly is in the Cartesian coordinate system. Do not try to sum up individual components in the cylindrical because only the Z direction is the same. Rho direction and phi directions depend on the position of your point. And in the spherical system, even more. all three directions depend, and coordinates depend, the directions of your field depend on the position of your point. So if you have a point, if you have two charges, for example, all right, so if you have one line charge from here, infinite line charge, Q, everywhere Q. I mean, in fact, it could be Q per length, all right? So because it's a line charge, so it's gonna be Q, line density. Line density. And then you have another one. So this is line charge density. And let's assume that this is another line charge density. And then this is minus Q sub L. And I want you to find the field at this point or along this line. I want to find you the field along this line. Then ideally, you can find the field from one line charge. You can find the field from the other line charge. And then you could try to sum up. Then I would suggest don't do it in the cylindrical coordinate system. I could do it because I will pay attention to the change in the direction, or but you will make a mistake, especially in the spherical system. Let's assume you have a point charge here, Q. And then that you have a point here, A. And let's assume that you have another point A, a point charge minus Q, and you have this point A in the same location. And I'm asking you to find the total field at A. Okay, you would have one component coming from the field along here. And according to that, it will be along the R direction, all right? And as a matter of fact, will be Q over 4 pi epsilon naught in free space. It will be R over magnitude of R to cube. And the other one would be here along that direction. And it would be ER, which is gonna be minus Q 4 pi epsilon naught R over R cubed, where this is R and this is R. So practically I have to take them, put them here. And here. The two R's are different. It could be different both in magnitude and direction, definitely. So you cannot sum them up the way they are here, because one direction is here and according magnitude, and the other is here for the electric fields. In fact, the other one is green. So you cannot sum them up like that. You have to decompose them in Cartesian coordinates to do this. So I would have, first of all, to do this line, and I would put my coordinate system at this center, and one point will be like this, one X will be Y, and then I would make my Z go through A to make it simpler. And then I would have from these two relationships to develop my field in X, Y, and Z for one, my field in X, Y, and Z for the other, and then sum them up. And what did I do, which is also important if you look at these two? I placed my coordinate system in a way to simplify things. So how many components does blue EA have? In the new coordinate system, how many components does it have?
Does it have two?
Yes, only the A, the Y, and the Z. How many the green E has in that?
The same ones?
Yeah, the same different direction, obviously, all right? But the same, EY and EZ, the green ones. So now if I place my coordinate system carefully, I can even simplify the problem, because the worst to do is to place your coordinate system so it's not in the middle of the line that connects the two charges, but somewhere else. In that case, you will have each of these fields will have three components. Well, it will be on a different plane, not necessarily three components, but it will be more complex. I made a mistake. Well, it depends on how you place it, all right? If you place it offside, if you do, yeah, it could possibly have more than two. It will have three components if you place it arbitrarily. But a lot of times we try, first of all, you recognize that in a problem like this, you cannot sum them up. You cannot sum these two up. No, no summation, not sum up. No. After you recognize that you have to go to only one coordinate system where you can reliably sum all of the components. And that's the XY, only in X, Y, and Z coordinate system. You can sum up components. So you have to move there. And then if it's up to you to set the coordinate system, then you set it in a way that simplifies things for you.
Professor, can I make just one clarification?
Yes.
Can you go to the first graph you drew with the cylinders? Okay, so if we look at the vector at P,
Yes.
and so let's say that we keep the rho component and the Z component the same, but we increase the phi component, what does that do to the vector? Does it move it along the circle, or?
No, it does not. So that's a different question. Let me go here and I will do this for you. So let's assume now that we are in a cylindrical system. Let me see. Make it a little thinner. Okay, cylindrical system. Here. Here. Okay, so I'm trying to reproduce the piece here. And then I have a Z direction. Let me do this direction here. Okay, Z. So here I have E rho. I'll make them a little big so you see them. E rho. E phi. They're perpendicular, all right? And EZ. So you want to, and then let's assume that the sum of these two was vector, the three, excuse me, was this vector. All right, let's assume there was this vector. Now you want to increase only your E sub phi, all right? So in fact, to find this vector, let me do it more carefully. To find this vector, I would sum these two, find this, and then I would sum these two, and I would find. So that is my initial vector. Now you want to increase this sub phi, and I will increase it. So your E sub phi will increase it a lot, so you can see it goes there. Now I'm trying to recreatively. So I find the sum of these two, which is this one, I will then find, and it will be in a different, obviously, direction. I will find the sum of these, which is now going to be this one. So that's what we have.
Okay, so then E sub phi just moves the vector along the tangent of the cylinder? Is that what's
Yeah.
happening?
If I move the vector, so the vector, if you move only one component, so the vector turns towards the component that grows. Is that your question?
Yeah, I was just wanting to know what would happen if like E sub phi changed.
Yeah. So for example, to see that, first of all, let's start with E sub phi and E sub rho without having Z. You
Mhm.
go to polar coordinates, like if you take the center, this one, which is the center circle, the equivalent to that would have been that your P is here, all right? And then that will be the center of the circle where the Z-axis goes by, and that will be your rho, and that will be your phi. Let's assume that now I increase phi. If I have them this small way before I increase it, if I have it like that, then, wait, let's put it this. Then the combination of these two is this vector. And then I take this vector and then I combine it with Z. But if I increase E sub phi, I double it. And then this vector that you have here, which is the sum of your original two, E sub rho and E sub phi, will now change and your new vector is going to come here.
Okay, I see.
See? And then I have to take and take that and then combine it with Z, but it turns, it is turning the total field.
Okay. That was all I wanted to clarify. Thank you.
Okay. Any other questions?
Sorry, Professor, just a clarification. When you say combine that summation of those phi and rho vectors
Yes.
with Z, what do you mean? I mean, like, how would you do that? Combine
Okay.
it with Z because they're
Yes.
perpendicular to each other. So
Yeah. So now I did this. Let me go then. The circle, it would be in reality is this green one here. All right. So it's this circle, the blue one is this green one. So now I'm going back to its original shape. And what I will do, I will erase, I will do it here. So I'm going back to the cylindrical now. Cylindrical. Here. There. My point now, this is the Z-axis now. Z-axis. Okay. Now, point P, this is the center of the, I mean, this is where the axis, the Z-axis goes from, and this is P. And now, according to what we found down there, P, according to that, this is the new vector, the green one. So this vector, it goes here and becomes this one, okay? And now the z vector is always like this. Your z vector is this one. So I'm placing now the z vector here. And now I sum these two vectors. It gives me that one. Okay, so if I call it this the sum, this is the sum of E rho plus E phi. Okay, and let me call that E1. Then if this is E1 and this is EZ, then this is the total field, which is E1 plus EZ, but E1 equals to E rho plus E phi plus EZ. Is that your, was that, am I responding to your question?
Yes. Okay. Thank you.
Okay.
Yeah, that's all I really need. Thank you.
Okay. You're welcome. Any other questions? Okay. Yes, go ahead. No, go ahead.
How do we know what mu is? I guess it's pertaining to the homework. How do we know what mu is?
Okay.
Is it a constant or is it?
Mu is always constant for the medium, unless I tell you that there is a change in the medium. If I don't say anything about the medium, is mu naught. So let me write it. So let me also say that for a medium, for dielectrics, we have dielectrics, we have magnetics, magnetic materials, and then we have air. So these are the three types of materials that we have seen, okay? So air has epsilon naught, mu naught. Dielectrics have epsilon, which is epsilon sub r mu naught, and mu naught. Magnetic materials have epsilon naught and mu, which is mu sub r mu naught. And epsilon naught and mu naught are given in the book. So epsilon they have been measured for air. And epsilon naught is 8.85, and I think there's a 4 after that, I don't remember, times 10 to minus 12 farads per meter. And mu naught, I don't remember that exactly. Let me see how much it is. Mu naught is...
I think it's 4 pi 10 times 10 to the negative 7 henries per meter.
Yes, exactly. Thank you. 4 pi 10 to the minus 7 henries per meter. Now, if I have another material, then I have to give you epsilon sub r. Therefore, for a dielectric, for a given dielectric, epsilon sub r is given. I will only give you that one because the other two are in the book. And for a given magnetic, mu sub r is given.
Okay, thank you.
Sure. Any other question?
Excuse me, Professor?
Yes.
I have a questions grounding. So how does grounding, for example, a coil, how does it affect the charge distribution? Like when we draw like the coil or something and just like try to distribute the charge, like how does the grounding it, how does it differ?
So let me say, we use the name coil for currents. When we have charges, we use the name conductors. All right.
Right.
So
Yeah.
if I were, no, that's okay. I mean, I'm just telling you so you know that if I say I'm giving you a coil of some sort, then you would expect me to say how much current flows through. If I say that I'm giving you a conductor, then you would expect me to give you the charge. All right.
Yeah. I'm sorry. I was mistaken. I meant a conductor.
Yeah, no, please. I mean, as I said, I do that because I know you know this, but I wanna just make it. It's my opportunity to everything that I have to tell you. I'll try to make it very. It's not like that. I think you do not know it, but in any
Thank you. Thank you.
sure. So well, remind me. We talked about the outside. So okay, you have now a charge. Let's assume that here you have a charge. And then around this charge, I have two charges. One plus Q. Let me see. How am I going to do that? I will put, for simplicity, plus Q, and for simplicity, minus Q. And now I would like to shield plus the two charges. All right. The best way to shield the charge, because it's like every charge, like a point charge like this, has spherical symmetry. All right. So the best way to shield the charge is to put a cylinder, a sphere, a metallic sphere. In fact, let me do that. A metallic sphere, okay, which has some kind of a thickness, like this. And what I do, I not only just place it, I also put here a ground plane. I put a ground rather and connect it. Now, what happens inside the metallic shielding sphere? Since I have a positive charge at the center, positive, all of the negative charges, all of the electrons in the metal will come and align themselves uniformly here. Okay, in the metal, but on the surface of the metal. And then without the grounding, if the electrons leave the nucleus, then all of the so what happens is the following. Let me assume that here, this is the thickness of my conductor, because I never said that, and then people can think. So let's assume that this is the thickness of my conductor here, all right? So my sphere, rather, the thickness of my sphere. So here it is. So here you have a positive charge, right? And then here you have, let me put a nucleus, all of the nucleus, and then electrons. Okay. And let's do two lines of those. So in the atoms of the metal, when now there is no charge, if I were to remove the charge from here, then practically I would have this in, they will be neutral. All of the electrons will be moving around there, even the free electrons, somehow they will be in there, but they will not do much damage because, even they will be somehow moving around their own atoms. There is nothing, to disturb them. If I put now a positive charge here, Q, that because of the electric field, all right, and how would the electric field go? the electric field would attract all of the electrons because it's a positive charge. The electrons, which are negative, have a negative charge, will be attracted to it. So this electron from here, which I would do green, this electron from here is going to leave. The ones that are closer is going to leave and come here. The moment this electron leaves, it leaves a hole in its place. So here, okay, so let me see here. It's going to leave a hole. And let me do the hole with purple. Now, let me do all of the electrons like that. Okay, these are all the electrons. Now, and also this one is going to move here on the surface, and it's going to leave a hole behind it. Okay, then what happens? From the next atom, this electron also moves and jumps here. And then, so this electron moves there, and it leaves a hole behind it. All right, so it goes, and then also below the same, there, and it leaves a hole behind it. And then this one is gonna jump, the other one, from here, there. It's gonna go there. It's gonna leave a hole behind it. Okay, so this one is gonna jump there. Okay, and it's gonna go there. Let me see. It's gonna leave a hole behind it. Okay. So all of the electrons will go on the front end and they will accumulate there. And all of the holes will be at the back end. And so the way we show the holes will be like here. All of these holes practically would be at the back end of the metal. All right? So that's why we have all of the electrons here, the green ones to be here. And then we have all of the positive holes, because the holes are positive, all right, to be out here. So these are the positive charges all around it. And then what is going to happen? Two things will happen. If all of the, if I keep that outer surface of the metallic conductor, which is my shield, if I leave it like this, the way I have it now, without any grounding, all of the positive holes here, they are going to feel the electric field from the negative charge from here. And all of the holes will accumulate here. So they will move, holes will move. And then from when I say moving holes from there, that means that some electrons will move in those positions and they will be floating away, because if the electrons, if there is any electron that has been left out there, if they see the negative charge, will try to move away from the negative charge, leaving behind them all the holes. So the holes will accumulate here, the positive charges here, and they will leave all of the other places. So you will have that, which then, the total of this charge here, the total of this charge here will be Q. So practically you put there the metallic sphere to accommodate your, to isolate your Q, and then what you did, the only thing you accomplished is to bring your Q closer to the other charge. So you fail totally if you stop there. So what you do is you connect this to the ground. And when you connect to the ground, then all of this, the ground is a sea of electrons. It's like a sea of electrons. You connect, all of these electrons see that there are these open positions here, and they fill them. So when that happens, all of the holes disappear, and the outside metal has no charge. So in that case, you have been successful in isolating your plus Q charge from the negative minus Q. Was that your question?
Yes, yes, this was very helpful. Thank you, Professor.
You're welcome.
I have a
Anything?
question.
Yes.
Just a question following this. So when you had the charges on the outside, was the plus Q, was it only on that specific arc length that you circled?
Well, they will be mostly there. They will have a distribution, all right? But they will be mostly facing the minus Q.
Okay.
Now, if the minus Q and the plus Q, and if the area of the spherical conductor you put there, they are, so the distance between plus Q and minus Q, this distance, if this distance is comparable with this, then you cannot solve the problem easily without the charge, without the grounding, because you will have, there is going to be a distribution of charges. So without the grounding, for example, let's assume that I had, let me do this, double this, duplicate. Here, let me remove for a second and assume that these are relatively accurate, the dimensions. So I'll remove this. And now what you will see in this case is all of the positive holes here distributed. If you look at the distribution of the holes of the charge from, say, this point to that point, what you're going to see is like a Gaussian distribution, where the peak of this will be around this axis. Okay, so it will be point, say, A. And you don't know exactly what it is in this problem because it depends a lot on the diameter of the spherical, of the metallic sphere that I use to isolate the charge, and of the distance. So whether the distribution is going to be like what I have here, or it's going to be like this, it's going to be Gaussian, but whether it's going to be like this or whether it's going to be like this, well, that's green. Let me see. You don't know until you solve the problem, and to solve this problem it's not easy. We don't know in this class how to solve this problem, to solve the real problem. However, if this is D, if this D, and this distance X are comparable, say if D is smaller than X, but not much smaller, all right? So they are comparable. However, when my sphere, if, I would say here, if D is much smaller than X, all right? So I am at this point, my negative Q, and this is a tiny bit of a sphere like this, and inside is the other Q. Then practically, if this is the D here, it's so much smaller than X as it was in the homework, then practically you can assume that all of the positive charge is here. And this is plus Q. You consider it concentrated. And then you can solve the problem then. But if it's not like that, then the problem needs to be solved accurately, and then we are not going to do it in this class. These are problems for higher level electromagnetics classes.
Professor, we're gonna solve questions today, like for the exam practice, but we didn't have time because the questions are.
We did not. So tomorrow I'm gonna do it, and tomorrow evening, and tomorrow afternoon.
Okay.
All right. So tomorrow, since I'm gonna be in class, I will give you specific examples that will be similar to the exam, to the midterm, and tomorrow afternoon the same.
Okay, so these kind of like a practice exam problems that we should focus on, right?
Well, and of course the fundamentals, all right? That's why I think what we did today was important.
Yeah, it is, certainly it is important, but what I was saying, should we, focus on these problems like for practice, preparing for the
Of course,
exam?
in what I did today, I think is important for you to keep in mind. But because I may give you some problems who have elements of it.
Right.
So, but tomorrow I'll give you more specific examples. You'll get a sense of how it will look.
Okay.
Tomorrow you're going to get a sense of how the midterm will look like.
Is it possible that you would, post just the questions before the class or before the office hours on Canvas? They're gonna go over
Excuse me, what questions?
the problems that you're gonna, solve tomorrow.
To put them ahead of time.
Yeah, so we can look at them and, keep in my notes so we can take notes behind you.
For me to put it ahead of time on 8 tomorrow, that means I have to finish them tonight.
Oh, okay. I thought if they were ready, I thought you.
Well, I have ready, but I may want to give you some different ones. So if I am to use something from previous years, I have them. But I may want to do something different too. And if I have them, if I finish them tonight, I will do it, but I may not be able to do it, ahead of time. I can put them immediately after. Now you say, well, what if I have no questions? Then if you can come into the afternoon session, that will be good.
Okay. The reason that I was, wanted them to see them before so we can just kind of like think of them before.
What you're saying, but I just unless I give you what I have, which I can do, but I may choose to solve something different.
Okay, it's completely up to you, Professor.
Okay, all right.
Thank you.
Sure.
Professor?
Yes.
Just a quick question. So I can't find it in the syllabus, but I'm pretty sure you said it. Is this exam open note?
Everything open.
Okay. Okay, that's fine. Thank you.
Everything open. I'm not gonna, the only thing that I would like you to do, and we can talk about this, is not to talk to each other when you solve the problem. But work on your own. That's what I mean.
Right. And I guess that leads me up to another question. So we're supposed to have our Zoom camera on and show us doing the exam?
It would be nice to do that.
Okay.
Now, if, however, you want to turn it off, you can turn it off, but everybody will ask everybody to sign that they have not received help from somebody else. And that's okay with me. I have to tell you one thing, and as opposed to other faculty, I really feel that I don't want to police anybody. I'm not the police here. All right. It's not to, if people, I have to tell you, I was a student. I knew who was using all of the techniques to, I mean, you cannot stop anybody who is committed to violate the rules from violating them. And I'm not going to make the conditions unbearable for the rest of the class to just prevent one or two, if any, people who would like to violate the rules. So it will be nice to keep it open. You want to turn off the camera, turn it off. You will have to sign something that says that you did not use, sign it, that you did not use, they call it the Aggie honor code, that you did not use help. And if anybody is willing to violate that and still sign the honor code, you know, this person may get a good grade out of this class, but they're not going to succeed in their life and work if that's how they work. And I think that we are all adults right now, and I'm not going to police anybody from doing this. I know that other people do everything that I feel it's such a waste of time for faculty and for students, for faculty try to police students for not from violating the rules. And I said, no. I mean, in your age, we ask you to go to war, you vote. Why would I not trust you that you, if you are committed to do something, you're going to do the right thing. And if you are committed to do the wrong thing, you're going to do the wrong thing. So the way we trust you to go to war, and the way we trust you and to sacrifice, and the way we trust you to vote your conscience, I will trust you that you will do the right thing in this class. So that's why, I mean, you're not going to see me policing anybody. You may have all of your cameras on. Do you think I'm going to look at each one of you? I'm not going to do that. That's my, sorry, I mean, my sound kind of not appropriate, but this is my policy.
Okay, thank you.
You're welcome.
You still have enough time for a question on one of the previous homeworks?
Sure.
Okay, so I wanted to ask on, I think it was on homework 4 on the second part when it's relating to the triangles.
Homework 4, let me
Yes,
just
homework 4.
here, 1 second. Homework 4 with solutions.
Yes.
Where is homework 4 with solutions here? Do you remind me? I don't seem to have it, but I'm sure I have uploaded them.
It's on Canvas. It's the one with the 2 spheres and one of them is shielded.
Yes.
Wait,
Yeah, that's very similar to what we did here.
actually, I think it's,
Yes, it's that one. That's the homework.
wait, I don't think that's,
That was for other class. So maybe that's,
it was with circular loop and a triangle.
yeah. Was it?
Oh, wait, never mind.
Yeah. So, okay, let me go back for a second and I will find it here. One moment. So, go back, homework, go back. This one, homework. 4, let me see, where's 4? 4. That was 4. Unless I have made a mistake somewhere. Let me see. 4.
When it shows up for me. For me, it's the title individual
It's 3 o'clock.
44502.
Yes. Okay.
With solution. Yeah, I think that should be what it is.
Let me see. Yeah.
Yeah, that's what
Okay, good.
So my question was, it was on the second part, like relating to the triangle. I know when it's solving for like the first side of the triangle, it has the equation, or it's for the AB side of the triangle for the electric field. It's solves it, I think, with the Q over 4 pi epsilon naught over the
this one.
Yeah, that one. So what I'm unsure about is the like 2 sine of A. I'm a little confused on how that got
2 sine
equation.
Let me get 1 second. Let me, 1 second, I'll tell you. I'm trying to find the formula from the book so you can make a reference.
I think the two sign a sub a comes from like the fact that you can like use the essentially the center of the line, and because the angles are equal, the differences should just become like 2, so it should simplify to like the infinite line case.
So there is, I found it on page 121 of the book at 4.3 section. It talks about a line charge from a section of a line, and it has a formula that gives the rho component and the z component. And the rho component in this particular case, if you see how it defines the rho, is going to be, let me see. Okay, so from here, and it's along that direction. All right, the rho for this one is the z component, all right, for me. So the rho from the book, if you reorient the section that the book has with that, so practically the z component has here a sine. It has a sine of one angle minus the sine of the other. But the two angles have a difference in sine, so it gives 2 sine. That's where you get the 2 sine of the angle A. Because you see these two angles, A sub A and A sub B here?
Yeah, I see them.
They are equal but opposite directions.
Okay, and then so because they're signs, the
They-
sign doesn't matter.
Yes.
Oh, wait, so
Because the negative sign of the angle in a sine makes a negative of the sine.
okay, and then so because of that, you just add them together. It's
Yeah. Yeah. Yeah.
Okay, that makes sense.
Yeah.
Okay, thank you.
You're welcome. Any other questions? Okay, so tomorrow morning, I will come with a selection of examples that will give you an idea of what I'm gonna give on Wednesday. And in the afternoon, we'll solve problems, similar problems, okay? So I will see you tomorrow morning for those who are in the morning, or tomorrow afternoon for those who are in. Okay. Enjoy the rest of the day. I'm recording this area, so I'm gonna put the recording up and the solutions from today. I mean, whatever, the notes rather. Okay?
Professor,
Yes.
I was looking at some of the notes, and it says that they're unavailable. Like some of the Gauss's law notes, it says that the file is part of an unpublished module and is not yet available.
Where is that? Let me see. Just a second. And in what, remind me the section you are on?
502.
Okay. So you see what I'm seeing to guide me a little bit.
Okay, it was like a February 1st lecture.
I hear it. Lecture now.
Yeah.
That one.
Yeah, I don't think that's available for me for some reason.
Okay, let me see.
Let me try again, just to make sure.
I need to check something.
Yeah, when I clicked that same link, it said it's unpublished, an unpublished module.
Okay, just let me see. I'll tell you how else I can do it. Student view. Ah, why?
It's like that up until February 8th. February 8th, I can see again, but between that little gap,
Yeah, let me see. You know, that's the problem with the Canvas. I have to go in the files. Let me see modules. Ah. Ah. Okay. But module 3. That's what it was. You should be able to check it out.
Okay, thank you.
You know, it has so many places for this green. They have like 10 different places for this to be published. And if one of them is not, then they don't show it.
Yeah, it's available now.
Okay, perfect. Thank you for telling me. Thank you.
Awesome. Yeah, thank you. All right, bye.
Okay, bye-bye.